Okay, so it's really a pleasure for us today to have Alice is the correct pronunciation, Cicirello, visiting us from the University of Cambridge. Alice has been here since yesterday, actually since Saturday. We had some enjoyable time. She had a very productive visit also with our group, which we hope leads in future inspirations as well. A few words about our speaker today. Alice is currently faculty at the University of Cambridge in applied mechanics, and she's also a fellow of the Churchill College at the University of Cambridge. She has a very interesting mobility journey. She obtained actually her PhD from the University of Cambridge, then became a Marie Curie early stage research fellow and research associate at the same institution. She then had a relatively short stint at the in practice at the industry, working as a senior research scientist at SLB, and then returned to academia, first to the University of Oxford as a lecturer, then an associate professor at TU Delft, and then back to Cambridge, I guess, where she started from. In the course of these experiences, she has held multiple positions of trust, including an editorial board member at the Data-Centric Engineering Journal. She had a number of fellowships and multiple other accolades that I will not exhaustively list. I just want to say that Alice is a very active member in the society. She has been organizing multiple events, almost pioneering initiatives like the Tandem Research Seminar Series, which I very much enjoyed. And she also maintains a page with very useful advice on academia and related things that I invite everyone to check out. But in her spare time, or maybe in her core time, she also does great research. And this is what she's here to discuss today. Specifically, the title of the talk is A Physics-Enhanced Machine Learning Perspective to SHM. And with this, I will give her the floor.
Thank you so much, Eleni. And yes, I'm going to talk about what I do in my spare time, which is usually most of the time. That's what I hope when I'm not ice skating with Eleni or singing with Eleni, apparently. So you deserve that. So, okay, so let's start with this. In my research, I'm usually interested in a broad range of structure. What you see here are actually bridges, satellite, but you see also drilling tools. You see, I'm
going to try to make it more of a full screen, but
okay.
maybe not.
I can wait.
I have been unsuccessful. I will return it.
Thank you. So you see a broad range of structure. What they have in common is that you have a broad range of loading acting into them. There is different. It's coming from operation. It's coming from the environment. And what we do usually as engineers is that we build model, and the model can be of different complexity, right? It can be a single degrees of freedom to a fully detailed finite element model. And what we try to do with this structure is that, of course, we monitor them because we would like to understand better how they behave in operating condition and to plan maintenance. But the information that we have are not only data that come from sensor, are also actually reports, text, and other type of information that might happen maybe from failure investigation. So what I'm interested in are actually three grand challenges, and these three grand challenges can be summarized as this. I'm interested in what can we do to design better engineering structure, accounting for uncertainties and nonlinearity, but how can we monitor actually also this structure for assessing the remaining useful life, taking into account that the fact that we just do not have uncertainties and nonlinearity, but usually we have sparse data. And then if we would like to leverage actually machine learning technique, one of the biggest challenges that we have is making these techniques explainable and interpretable so that we can actually make decisions based on that. Okay, so how do we tackle these three grand challenges? What we do is actually have an integrated approach. And what it means is that we go in the lab, we do the test, we build a physics-based model, we do the uncertainty quantification and develop technique for uncertainty quantification, but we also look at how to extract information, but also how to integrate physics with data and with uncertainties and everything that we can learn from the system. And this will be the topic of this presentation. But just to give you an idea, what we basically do is that we develop this technique for exploring innovative design. We develop technique for assessing the system performance and also integrating, extracting and integrating this information. Okay, so I'm telling you all of this, and it sounds that it's all scattered, it doesn't make sense. So I'll try to make sense of this and why this is important by giving you some example. For the information extraction, one of the key challenges is, for instance, that one of extracting information from documents. And what we did there was developing a self-supervised classification approach to sensor failure and to understand how we can actually learn data and how we can learn patterns from sensor failure so that we can distinguish it from operating condition. But also how we can extract information in the sense that we have a corpus of documents and now we can create directly graphs that connect things automatically. And this is very important in system engineering diagrams. From this part, then I'm going to talk of physics enhanced, but what we've done very recently was developing technique for doing probabilistic model updating, actually. Looking at transitional ensemble Monte Carlo, cycle of VBMC, variational based Monte Carlo. And the idea there is how can we actually apply this probabilistic technique to actually be implemented in engineering when we have usually challenges due to the size of the problem or to the number of uncertain parameters. And we're looking also at the forward uncertainty analysis. We recently explored techniques for interval propagation in precise probabilities, but also look at damping. And all of this, again, is important because if we would like to use this knowledge to guide the decision-making at the design stage and operating condition, if we don't know all of these things, if we cannot extract the information, update our system, propagate uncertainties, and understand the real physical behavior, then we will not be able to do to support engineering system. But of course, there are also other crazy stuff that we do in the group, and some of these are shown here. So what you see there, these are two collaborations with the zoology, the biology department now in Oxford. And one of the cool things that we did was looking at plant hoppers that actually are sort of twerking. So the bottom part is vibrating quite quickly. This is a nice speed camera video, so it seems that it's going much slowly. But what we did there was investigating how this vibration was generated and building a mathematical model. And we also look at spiders, actually, and how to build model for that. Okay, so this was to give you sort of an idea of the research landscape and all the different things that then at the end lead all together to physics enhanced machine learning. And my presentation will be structured in these 4 parts. And basically, I will talk about why we need physics enhanced machine learning. And then I will tell you about what are the main strategies and how we tackle some of the challenges. And then I'll tell you, in my opinion, which are the most pressing challenges in this area. I usually say at this point that if you have any question, you can raise your hand and I'll stop. But Eleni was suggesting to keep this for the end of the presentation. Okay. So I know that I'm preaching this to the right crowd in a way, but of course, you know all of it. What are the goals of structural health monitoring? We would like to track the health status, and that means that we're going to have data and signal processing, and we would like to make inferences on the health condition or our structure. And again, the reason is to guide decision making. So these are the sort of 3 main steps. And of course, when we are at this level of making inference, what we want to do is have models that help us detect patterns, models that detect presence, location, extent of type of damage. But also we would like to develop digital twins. That would be the ultimate goal. A model that evolves with time and create a digital replica of our system. So why is machine learning important? And then I'm going to build up and tell you why physics enhanced machine learning is important. Well, if you have machine learning techniques and you use it for structural health monitoring, you are now in a position in which you can extract and summarize information from large data sets. You can learn the patterns, and you can inspire even development of new experiments to monitor the structure in a better way. So this is already some very key things that can help us in structural health monitoring. Of course, given that we're going to develop also a model to make inferences, these techniques can help us also reduce computational cost of the digital twins by developing so reduce order model, but also developing models directly from data. And at the end of the day, if we would like to do this online and make inferences online, then machine learning becomes, again, very important for our efforts. Okay, one of the key catch is that machine learning relies on data. But data is not enough, actually. It's actually information that we care of. Because one of the things that we always assume, and we don't say much about it, is that we make some inherent assumption about the available data that we would use in SHM. And the inherent assumption is that they are informative. So there is not just data that is randomly collected. There is actually something that will help us understand some specific phenomena. Should be accurate, and so we have to make sure that the sensors are calibrated, there is low noise level, but should be also reliable. If it doesn't satisfy these three criteria, then the data is actually not a good data to build a data-driven model. And of course, if you think about machine learning for information extraction or to build models that are based on data, everything will be as good as the data. So as soon as we don't comply with these three, we will not be able to do much, but also we should be able to have a data-driven model that actually resembles what is happening in reality. We should be able to characterize all the different states of the system. And most of the time, it's difficult for us to observe all of them. Imagine if we have to observe all the damages in a bridge. We cannot go and damage the bridge, as simple as that. So that becomes already complex. But also we should label them. And of course, data can come from heterogeneous sources. It's not just the sensor measurements, it's the report and its features, and it's everything that you can get even from expert knowledge. And one key thing as well that we have to remember is that the data must be up to date. We should trust the quality of the data. If we just given data and we cannot trust the data, or the data is historical data that is being monitored in different ways with different conditions, we should be aware of that, because otherwise we will have data biases and we will have problems with the way we process the data. Okay, one key thing that I mentioned is that in a way, to support decision making, we should go beyond these black boxes. We should go beyond using just machine learning. And the reason is that we are actually trying to make these methods interpretable and explainable. What I mean by that is to answer these two questions. How was the prediction made? Is something is actually happening and we have to make a decision? Can we communicate this decision to support decision making? And if you think about it, what interpretability boils down to is this question. Can we understand why the model would succeed, fail? And the main reason is that if a human has to take a decision and has to make sure that, things, are going to work in the future, that person would like to know if things are failing, why they are failing. That's pretty much the reason. And if you think about communicating prediction, we would like it to be comprehensible, but also we would like to quantify any remaining uncertainties. Uncertainties become key now, because we would like to communicate how robust is our prediction, our inference. And of course, this is important because the critical decision and the uncertainty associated with that should be understandable by humans. Okay, so I'm telling you all of this, and machine learning is great, and it's an amazing technique that has been helping us in doing many of these tasks. But the title of the talk was Physics Enhanced Machine Learning. So why this is important? I already mentioned to you the problem of the data. And if you think about it, we can actually try to describe this about what is the physics knowledge that we have of the system and which is the informative data availability. And if you see in this graph, we will have 9 areas with low, medium, high physics knowledge and low, medium, high data availability. And machine learning will fit right here. If you have the correct data that is informative and we have very little knowledge of the physics, we will go all the way machine learning and use data-driven techniques. In a way, if we have very little data that is available, but we have lots of physics knowledge, we might go and prefer to use physics-based model. But most of the time, we are actually in a condition in which we have data, we have information about the physics, and actually physics-enhanced machine learning is populating much more of the space that you can imagine, and it is actually, as shown here, taking quite a lot of this space. And the main reason for this is that every time we think about machine learning, we have to think about the volume of useful measurement, of useful information. But also, remember one thing that I told you, the data should be sort of representing everything that has happened to the structure, that will happen to the structure in the future. But if it doesn't, then we would like to generalize to small, medium data regime or enforce physics constraint, we should embed physics. So that's also another reason why physics-enhanced machine learning is becoming more prominent. Okay, so one thing that I would like really to stress at this point is why machine learning by itself can be dangerous, and I will tell you also why physics by itself will be dangerous. If you think about it, that generalization and extrapolation becomes important, but also observational biases, right? If your data had bias, if it was corrupted, the model will be based on that data. But also you can have physical inconsistent or implausible prediction. This is actually very interesting. Your data-driven technique doesn't know the physics law. So it might give you something that it might be completely wildly wrong. And again, this can be caused by having corrupted or non-informative measurements, but it can be also due to the fact that we are not necessarily embedding directly causal relationship, and we are not distinguishing necessarily confounding sources. So what it means is that we will get very accurate but wrong prediction. Great, that's what we want as engineers. If you think about physics, it's also dangerous, and it's something weird because as engineers we're trying to use physics-based model, but you have to remember again the assumption that you're making, because you get the generalization performance, but it's at the price of an expensive and time-consuming modeling setup, but also computational cost. In principle, with the model, you should be able to represent everything, which means they should know everything as well. And of course, you will get physically consistent, but it also can be not plausible prediction because maybe you're doing some simplifying assumption. You're removing part of the physics that actually was relevant. So this is then becoming, again, a warning to remember that it's not that one method is better than the other, it's that you should use it depending on the condition that you have and the information that you have. Okay, what I was telling you about is how to integrate this data and physics. And this leads itself immediately to what is called a digital twin, and how this digital twin, this model is evolving with time. And I decided to give a very simple example to explain the problem and why uncertainties become important and why that is very important for decision making. So let's imagine that we have a wind turbine and we have some true input. There are the operational condition and the environmental condition. Now, in principle, we will have a true response. We are never going to be able to measure the true response. We're going to have some sensor, which means that we're going to have measurements. And then we can build model, and the model is never going to be exactly a perfect model. It's going to be an approximation of reality. And then we're going to have also a model for the input loading, because we are not going to be able to characterize every single load on the structure. And of course, if we think about the input and the output that will come to this model, if we have this as an input of the model, we will have a y, an output of our model. Now, what we can do is to take the measurements and try to fit a model for that measurement, and therefore we will have a data learned response, let's say. But also we can combine the measurements and the physics, and we'll look at physics plus data learned. Now, what is interesting is that at every single stage, we are actually creating an error. And none of this is exactly the same as the other. Now, I'm going to try to explain this step by step, because this is key also, and we have to keep this in mind when we do structural modeling. So if you think about it, let's replace, so we have our system, there's the physics, that's our real system, we have the true input, the true output. Now we have sensor, we have an error because we have a noise measurement, a noise level, which means that we're going to have a wise measurement. And this is going to be the measurement error. Then we're going to have an approximate physics-based model that is approximate the part of the physics that we care about. And what it means is that we're going to have an input error because we're going to model that, but we're going to have also a physics-based modeling error, right? Because we are doing an approximation in our model. And then we can approximate our data-driven model of the data, and then we'll have a data-driven modeling error. We can now update the model with the sensor, and we're going to have a physics-informed modeling error. We have lots of error. We have lots of uncertainties that are coming in. An error can be unknown or random. And by unknown, I mean epistemic, so due to the lack of knowledge, or random because they are inherently there. They will be there no matter what, because they are due to a variability. And of course, we have also to remember all the time that model prediction that we'll do with this model might also be inconsistent because of the way we model the system, what we model. So in a way, we can think about uncertainties into these categories. The first one is aleatory, inherent variability, part-to-part variability, or sense of noise, temporal, epistemic uncertainties as a lack of knowledge. But then we have the model discrepancy, that in principle is reducible if you know what you should include in the model, but also model discrepancy due to data, and also that can be reducible. And these are called usually known unknowns, but you might deal with what are called also the unknown unknowns. There are actually irreducible uncertainties because you don't know those. They are there, but you didn't model them, and you don't know how to retrieve them. And some of them are irreducible because you cannot even get the information about them. But some of them may be actually irreducible as well for other reasons, because actually they're coming from model prediction, while these ones are coming from parameters. And if you're able to reduce them, they immediately become again known unknowns. Now, why this is important? It seems a trivial distinction, but this actually changes the way in which we frame the entire problem, or the way in which we account for uncertainties in physics-enhanced machine learning. So far I told you all the basic assumptions and everything. I haven't told you yet what is physics-enhanced machine learning or anything. So let me start by telling you about why this is dangerous, actually, if we didn't do this step, and why we should have accounted for epistemic or remember that. Because we might get a perfect model that actually, because there are things that we don't know, it actually is giving us poor model prediction. But it's also underestimating the overall output uncertainties. And again, it will lead to wrong performance. For structural health monitoring, what's the key catch? Well, if we do poor inference on future health condition, and we do decision making that are wrong, what's the point of doing all of it? And this is the dangerous things, and that's what we should keep in mind. Okay, so what is physics-enhanced machine learning? It's actually an integration challenge. And it is an integration challenge because I told you everything that we need. We need a physics-based model, we need data, we need to account for uncertainties, nonlinearity, and all of this. So it goes beyond the mathematical model and the noisy and gappy data. It actually accounts for the domain knowledge, the expert knowledge. Do I know what should I include in my model? Prior knowledge, do I have prior information about this? Or do I know first principle, then maybe I want to add as constraints. But also, do I have data that come from spatial and temporal resolution that are completely different? How do I count that in my model? And how do I account for the fact that maybe I'm assuming some physics, but it's wrong? And this seems, like, no, it will never happen. But it's so simple to have a counterexample. And it's when you think about joint structure and friction model. We can assume that Coulomb is the model, but that might be completely wrong. And that would lead to completely different results. We should deal with corrupted data, deal with the non-informative data, and in principle remove them because they will bias our model. We should deal with uncertainties and provide a strategy for validating the model. So it sounds, a very big challenge, and you guys, many of you here, are working actually on many aspects of these challenges, if not all of them, together. And if you think about it, what is the end goal and why it's important for engineering application is that we would like to get generalization performance in conditions that maybe we haven't observed. We would like to remove physically inconsistent or implausible prediction, account for uncertainty so that we can communicate that. And we would like to be able to explain and interpret our inference. And in case, if possible, informing physics. We would like to learn things that we didn't know before. That would be the ultimate end goal. Okay, so I hope this makes sense, why this is important, which are all the components. People are still smiling, so that's good. And so now I'm going to talk about which are the main strategies, because so far I gave you the context of why this is so important. Okay, so this is a very nice picture that many of you will know because it was done here. And this is a very nice way to give actually an example of all the spectrum of physics-enhanced machine learning techniques that can be done. Now, of course, you guys here are much better than me at explaining this, so I'm going to go for a sort of much lower resolution version of this. So bear with me. So let's start with this. We are engineers. And I've been telling you that we need to include physics and data and all the information. So the first question is, how much physics, how much data, how much actual information should we include? And how do we integrate this physics model, the domain knowledge, and the data-driven? In a way, you can think that there are many ways of doing this. So let's split them up in three simple ways. The first one is that I start with the physics and I want to integrate information that comes from data. We can call this physics-guided machine learning, okay? What we can do then is to say, wait, I start from the data-driven model and I'm trying to now constrain some physics knowledge. And we can call that physics-informed machine learning. But now we are also in a paradigm shift in which we might want to build a model that has actually both of them. So as a component that comes from the physics and a component that is a data-driven model. And this is the physics encoded machine learning. And if you read the paper that many of you guys have contributed to, you will see that this should match pretty well with that definitions. But now, how does it work and why this is important and why this distinction is important? Well, you basically start from an underlying physics model that you trust. You believe that the model is correct, and now you want to update your model, like model parameters, based on the data that you observe. So already many of you are thinking Bayesian inference, you're completely correct, because that's the framework that you can use there, and actually it's the main framework for it. And what you do have is a prior distribution, you have some prior knowledge, you have the likelihood that is looking at the discrepancy between what your model, physics model predict and what the measurements are telling you. And then you learn the posterior. Something that is very important to mention is at this point, for those of you not familiar with this, is that the posterior distribution is referring to what is called a latent variable. It's a variable that we cannot observe, we cannot test it. And what we are doing is that we look at what we can observe, the measurements, and we compare it with the noisy measurement, and we compare that with the results of the physics model. And now we want to update our knowledge of something that we could not observe. And the idea is that we would like to improve the performance of the physics-based model. What I mean by that is that we would like our model to now account for the things that we don't know and predict uncertainties. Great. So the focus is on how the physics-based model parameters can be updated. And there are many examples that are based on probabilistic model updating. And you can have also physics-guided neural network that can fall into this. Okay, so I hope that this makes sense and it's clear the core idea here. Then the other way of doing the problem is to start from the data, and then we want to basically add physics. And this is what you can call physics-informed machine learning. So we build a data-driven model, and now we constrain it. And we can have observational bias, inductive bias, and learning bias that help us constrain and enhance generalization. So the goal is to improve a machine learning algorithm, not a physics-based algorithm, okay? And of course, you can have different ways of doing that. There is physics-informed neural networks, graph neural network, and sparse identification with constraints that can fall into this category. And then there is the one that I was telling you, in which we have now data-driven model and physics-based model that are actually combined in some sort of ways in which we partially specify the physics and partially learn a data, basically, part. And one way to see this is to imagine that we have some physics bias, some noise measurements, and thinking about the fact that we know basically all the rest, for instance, of this equation, but we have an unknown functional relationship that we would like to figure out. And what we would like to do is improve the performance of this hybrid model, in which we have data and physics together. And of course, the focus is develop hybrid architecture and improve their performance. And in this, the gray box model, physics-informed neural network, neural ODEs will fall all into this. And I hope that Marcus and the others would agree with this definition again. And now I've been telling you about physics biases and the three ways, and the three ways in which you can do that with physics-informed neural network. But in general, you can think about physics-enhanced machine learning as a way in which you combine these data-driven techniques and physics knowledge and physics biases in 4 ways. And again, this is my biased view, and so remember, it's not set in stone, it's my opinion on this. The first one that is very not controversial is observational biases. What it means is that, let's say that we have a data-driven model, and we start from that, but now we have observation that comply with the physics, and we want to use that information. We can use directly that measurements that come from physics model to enhance our data set. We can also do inductive biases because maybe we know conservation laws, maybe we know something about our system, and we know something about invariances that we want to include. We can have learning biases, and by that I mean actually how the inference learning algorithm has been set up. How you define the loss function, how do you define actually constraints on the learning algorithm. But then there is the fourth category that is coming from the fact that now we know some part of the physics. Maybe we know part of the model, maybe we know the equation, and we have something that we don't know that is coming, then we will have to learn from data. And the model form discrepancy biases are actually on partially known physics-based model. And basically, we can consider that as parameter, then the part may have also parameters that are uncertainties and uncertainties, or just having uncertainty in that part. And of course, basically, all of these things, what they do is that imagine that you have a model and the prediction space was so large. Every time we put one of these biases, it's like we are limiting where the solution will go and where the solution might be. And basically what they will do then by constraining the space of admissible solution is that they will accelerate the training and enhance generalization, even if you have little data. That's the key thing with this. Okay, so it seems that I'm going okay. So for those of you that are not familiar with this, I'm going to try to explain it very briefly how you can do that, and then we'll have the introduction part of this presentation. That was half of the presentation. So this is an example of physics-enhanced machine learning architecture using pins, and it's a general sort of way of seeing pins. So what we want to do at the end of the day is having a partial differential equation that we would like to solve. And what we would like to do is actually, first of all, make sure that we are able to understand the relationship between the input and the output layer. And what we can do there is to use a multi-layer perceptron, so a neural network architecture, in which you have basically an input layer, several hidden layers, and then you get out an output layer that is for inference. Now, in the PD, in the partial differential equation block, we may retrieve operators or constraints on the output, and we can use autodiff to do that. And we might have this type of equation shape with some boundary condition and some initial condition. The interesting thing is that while usually, if you have just a neural network architecture, your loss will be comparing the output layer with some experimental data or some real data. In this case, what we are doing is that we are constraining the loss to actually conform with something that is being given by the partial differential equation. And you will have therefore a loss that will be combined by initial condition, boundary condition, and residual, or any constraints that you might have. And of course, if the loss is less than a certain level that you would like, you will just finish, or if it is not, you go back in the input layer and start again. So this is a very simplified way to see how all the biases are coming in, because there will be a bias that is in the observation, because maybe you want to introduce data that embody the physics of the problem directly here in one of the input layers. You may have inductive bias in the way you're actually choosing the architecture of the multi-layer perceptron that you're going to use. So maybe you want to use CNN, for instance, convolutional neural network. You may have learning biases in the way you choose this loss function, actually, or the optimization that you use. But also you can have discrepancy biases, because here, when you talk about the PD, there might be parts that you already know and some other parts that you don't know. So this is a sort of nice way to wrap up all the biases in a very visual way, or so I hope. Okay, so if you think about it and all these things that I was telling you, how can we then tackle the problem? Well, the problem is that there is not one physics-enhanced machine learning technique that fits all the problem. There's nothing. And the reason is that it will depend on the amount of physics knowledge, on the purpose, and on the complexity of the system. Those three things should be kept in mind all the time. And the amount of physics knowledge and versus informative data can lead you to use physics-enhanced probabilistic machine learning to something that is more on a neural network architecture. And I'm giving just 3 examples, just for the sake of time, of course. But also the purpose may be, do you want to identify unknown parameters? Do you want to quantify all uncertainties? Do you want to develop a digital twin? Depending on this question, you will choose a completely different technique. But of course, it depends also on the complexity of the system. Is your system linear time invariant? Is it actually non-linear time varying system, or a multi-scale, multi-physics, non-linear time varying problem? That will change how you address the problem and how much physics or much data, how much domain knowledge you need. Okay, so I covered why we need physics-enhanced machine learning in SHM, and I hope that I make a strong case for it. And I also explained to you which are the main strategies that you can use, and how you can go from the data to the physics or the other way around, or combine them. And I told you which are the trade-off of using one and the other. But now, how do we use these techniques within the data vibration and uncertainty group? And these are some of the people that have been involved with these projects. And I'm going to talk about some examples of this. So the first challenge that we were interested in, and this project was led by Yang Ku, is about spatial and temporal correlation. And I'm going to give you a striking example. So let's imagine that we have a bridge. The Yessel Bridge is a twin-girder steel rod bridge. And we want to actually update our knowledge, our physics-based model. Okay, so we have measurements, and of course, this is a very large structure, so we will have multiple measurements. Now, we can do control testing, and we can look at track passages on right and left lane, and we can measure actually strain at different location. One thing that we usually do when we do statistical model updating is actually considering that everything is IID, which means that we completely forget about the fact that the sensors are located at several positions and that the information that they have is correlated. Now, to make this extremely clear, imagine that you have two sensors, sensor 1 and sensor 2 here, and we are looking at the model prediction versus the data that you collect and the correlation between them. Now, if they are very close to each other, of course, they're going to be very much correlated. If they're very far from each other, then they're going to be less correlated. Accounting for this correlation will affect completely the accuracy in the way in which we will update our model parameters. Most of the time, we don't account for that. There are two reasons why we don't account for that. The first reason is that we should model this correlation. And most of the time, we don't know it. And the second reason is that we usually deal with large data set and computational demanding likelihood function. And to select, if we really want to select different type of model prediction error, we will have to account for the evidence. And most of the time with sampling techniques, we don't have that. Okay, so then we were in trouble, and we were using a physics-enhanced machine learning technique to tackle this. So what we did that was applying a physics-guided approach. So we say we have a non-physics-based model, so we can model the bridge with a model we can trust. And now we have a large number of noisy measurements, and we have a pool of candidate models for the spatial correlation. This is an inductive bias that we're going to give to the system. And what we have to develop is an efficient calculation of the log likelihood. Without that, we cannot actually go into the 10 to the 2, 10 to the 4 number of measurements. That will actually lead to very poor detection or anyway system identification of the model parameters. And we did this for multiplicative and additive model uncertainties. And pretty much what we did was saying, okay, we can build a physics-based model, we can look at candidate model pools, and then we can use nested sampling in which we use also this efficient log likelihood to have a posterior predictive distribution. This was a great way to start enhancing this technique by accounting for the physics, for the domain knowledge. There is the sensor placement. And we saw that it made a very large difference in the posterior prediction and in the identification. But of course, we are making some assumption. To make this efficient, we have to make an assumption on the model prediction error. And this is a limitation, and further work is currently being done in this area. So at this point, normally I will ask people if they have questions, but if there are no burning questions, I will move on. Yeah. Okay. The challenge too that we might have is obtaining a measure response states. So imagine that you have a wind turbine and you have an high risk of fatigue failure due to the loading. And usually fatigue spots are happening there below the mud line where we don't have way to measure the system. Or actually, we don't monitor the system. The other challenge is that loads are unknown. This work was led by Joanna, and it was done in collaboration with Liz Marie, that actually came up with the idea for the project. And what we did there was looking at a very interesting data set, because we had the Western Wind Park data set for these wind turbines, in which we had the SCADA data, and not only acceleration channels along the wind turbine, but also we were measuring below the mud line. And we had access to actually X-ray channels. And we had data that was collected across different operational stages as well of the wind turbine, which was very interesting. And so we had access to this very unique data set. And what we wanted to do was actually seeing how much Bayesian virtual sensing can be applied for this problem, and what would be the robustness with all of the uncertainties that, as I mentioned to you, will become very important. So what we did there was looking at what is this physics encoded approach. There is actually a Gaussian process latent force model. What it means is that we are having a physics part, and then a part that we don't know, that is the forcing, and we are going to use a data-driven approach for that. And in this case, it's a Gaussian process model. And basically, we take the data, we have to do some operational model analysis to do some system identification. That helps us build the physics model, combine it with the data, and then we have to go through the process of model tuning, and then we have a joint input state estimation. But doing that, we were able actually to make a prediction on the strain measurement, in this case is a position S2, and validate them both in the time and in the frequency domain. And this was one of the first time in which this framework was validated, and it was very exciting to see how powerful it is. But of course, it comes with some open question, because the modeling assumption that we were making is that the system is linear time invariant. Most of the time it isn't. So there are still so many things that can be done. But this was something very exciting in which physics-enhanced machine learning was extremely helpful. Okay, challenge 3 is actually identifying friction. And this is very important because it's a discontinuous nonlinearity. And friction is everywhere because you have joints and you have things that are rubbing against each other because of this joint. And usually it's very good because it helps dissipating energy and reduce vibrational amplitude, but it's also actually not good because of wear, noise, and the fact that stick-slip phenomena can reduce the remaining useful life and lead to sudden failure. Now, if you are not sure about what I mean by stick-slip phenomena, what I'm going to show you is the test case that we used, and I'll try to explain to you what is happening there. So this is our system. It's a very simple one-story frame system in which we have 4 bars, and then we have a top plate and a bottom plate, and we are running this system with a motor. And what we see there is the contact point in which there is a contact force between the brass system with the counterweight and the top plate. That is creating friction. And now our system is driven so that it can move, and then we will see the top plate that will experience stick-slip motion. So we'll get stuck and then we'll move again. And this will happen depending also on how the motion is applied to the system. So let me show you this thing here. So you will see now, this is first continuous motion of the system, so it's still moving. But now we have 2 stop stick-slip. So you can see there is sticking and then moving again. You can have 4 stops. And with this setup, we can go even as high as 12 stick-slip. Okay, so what do we need to do in real structure? What are the challenges there? The challenges there are obtaining the states, obtaining the friction force versus velocity curve, and looking at the force evolution and uncertainties, even during the stick-slip, because this is actually the problem. The real problem is measuring the stick-slip. And of course, if you think about friction, you cannot put a sensor in between the contact because that will change the contact. Okay, so what did we do there? We apply a physics and code approach that is looking at what is called a switching Gaussian process latent force model. So how does it work? We have part of the physics that is known, but we add also the data-driven part that is coming from a switching Gaussian process to model the latent forces. And now they are switching in the sense that they are accounting for 3 main states, basically. We have a sliding response of the dry friction oscillator. We can have the sliding phase, but we can have also a resetting mode because the latent force in friction will have actually to account for these sharp discontinuities. And again, this is coming from the fact that now we are able to solve these challenges because we are combining what we know from the physics with what we know from the data-driven in this physics encoded state. And we are using some different biases in terms of discrepancy, inductive, and learning biases. Now, how does it work? So basically, we start with the noisy measurements, driving force, and system parameters. We have to set up some settings about our model. And then we have our core engine of the switching Gaussian latent process, latent force model. And what we get out of this are this posterior distribution of the states, but also we get the nonlinear force. So what is key and what is very important for us in engineering is actually understanding this friction force versus velocity. And this work was led by Luca Marina. And what you see here are actually our prediction of the friction force versus velocity. And you see the data and what happened for different level of friction that we can actually observe. But also what you see here are the displacement, velocity, acceleration, the friction force, and how the model is automatically selecting to go from resetting to sliding and to sticking mode. And what you see here is that we are able to detect very accurately even the sharp edges, not only in the response, but also in the friction force and also in the friction force versus velocity. So this was, and this is done with experimental data. So we have both model and data. So again, this is great, but you can expect that I'm going to tell you also what are the things that needs to be done. And so, for instance, in this case, we just look at one type of nonlinearity, and extending it to multiple nonlinearity might become challenging. And of course, there are the dimensionality issue with the GP. Okay, another challenge is still related to friction law, and I hope that you're still with me, guys. And the friction law identification is something very important, because even if I get the FV graph, but if I don't know how to distinguish which is the actual law, then I cannot put that in my prediction model, right? It's as simple as that. But we have a problem here, and we can look at this very simple system. We should be able to analyze and understand this, right? But there might be a region in the parameter space of two different friction laws, like the Coulomb and this rate state law, in which basically the models are not distinguishable. The response, and you will see the mass displacement versus forces give this kind of plot. So we said, okay, if we are in the region and it's undistinguishable, can we find a way to go back and say, this is actually the law? That was our challenge. And again, we use physics-enhanced machine learning to solve that. And this work was led by Christos. And what we look at that, what we did there was looking at developing a physics-encoded approach. And the way in which it works is that we're gonna have a governing equation, and we say that we know partially this governing equation, so we know some of the linear part, but we don't know some functional relationship. And basically, we have some time series of noisy time series of data. And what we want to get out of this is actually the approximation of the functional form that we don't know. But we would like the functional form to be the correct one. So what we do is that we use what is called a CINDI, basically, approach, in which we have a dictionary of function. There is an inductive bias, because we'll say, okay, actually the things that we don't know will be obtained as a product of something that we might know that belong to this dictionary times some sparse coefficient. And then we look at a way to reduce the space of the solution by using Runge-Kutta scheme. And then we have another inductive bias. And then we can calculate this coefficient here, the sparse coefficient, that will tell us which are the parameters that matter the most or not. And how it works is that basically we will have one set of measurements, and from that, even for high noise level and discontinuous nonlinearities, for the first time, we will be able to actually detect and distinguish nonlinearities. And what is very interesting is that we are embedding here not only the integration, but also some physical constraints that come from the stick slip motion. So let me show you a case study in which we have this region in which it's impossible to distinguish the two laws. And we say that in our dictionary, the two laws both appear, so they are there. And now we're generating data by using as ground truth one law, and then we use the data by using as ground truth the other law. And then you can see what the PyCINDI is doing by inducing all these data sets. And you can see that we are getting very accurate results in terms of the equation. Remember, this part and this part is completely unknown to the system. You have additional candidate function, and the data set looks pretty much the same. So we were able to identify the correct friction law even in this inverse problem. But of course, we are making a big assumption. We are assuming that the parameters of these friction models are exactly deterministic and known, and we didn't know the functional form, but now we know it and everything is great. Reality is different, things change with time, and uncertainty should be accounted for. Okay, the last thing in which we can use physics enhanced machine learning, if you're still with me, and that's what we've been working on and we are working on at the moment, is super important, again, for structural health monitoring. And this is actually distinguishing aging to slow varying effect. So, I mean, aging slow varying effect to sudden fast varying damage. And Francesca, who's leading this project, came up with this very nice way of visualizing that. So, sudden failure versus aging phenomena that you see there. And at the moment, she's looking at numerical benchmarks, real case studies across different systems. And the idea there is how can we use physics-informed machine learning strategies to actually distinguish this fast and slow trend and have an architecture that can actually then help us looking at physics and varying phenomena. And of course, what we want to do is to leverage on existing physics that we know, even of the damage and aging phenomena, but also map this system to a lower dimensional state. Okay, guys, so I hope that now it is clear why physics enhanced machine learning is important, which are the main strategies, and what we've done in the group to cover this. Of course, I will not go into the detail of each single thing, because otherwise you will be sleeping in 10 minutes, probably because it would be too much detail. But what are the challenges and opportunities that are still open? Because there are many. One thing that I was telling you about was warning about the data-driven strategies and where the data is coming from. And remember that if the data has data biases, you might have accurate but wrong prediction. And dataset, this is a real dataset from monitoring campaign, can be noisy, not complete, and corrupted. So really you have to be careful with that. And challenges and opportunity are developing techniques that can automatically remove inappropriate biases, that developing metrics that can assess information quality, and integrating different information with different quality. If you think about the physics biases, what I was telling you is that the solution space will be reduced basically by adding these constraints. Let's look at very simple 2D representation. And let's say that now we are putting constraint and we limit our search here. And the approximate solution is there, but the correct solution is somewhere else. This is coming from the fact that maybe we should improve our physics knowledge of the problem, and we should have a way to detect and remove inappropriate biases. And again, as I was telling you, maybe having the wrong constituent model. This is a very simple way to see that. But also how to incorporate multiple physics models. And of course, the technical challenges are many, and they come from the nonlinearity. Where to measure, what to measure, what is important, the multi-physics, multi-scale problem. And again, this is a biased view, but there are even many more that you can think about that comes from the metrics and the visualization of the results, but even calibration. And there are even more that you can think of. So it's a very exciting field in which many things are happening and is fast developing. And with this, I would like to thank you for the attention. This is, if you scan this QR code, you will be brought to the website where many of these papers that were listed are there. At the moment, the team is actually quite small, and these are the people that are in the team. And the work that has been presented was funded partially by many funding agencies that are reported that I would like to thank. So thank you so much for your attention, guys.
Thank you very much, Alice. I think it was a great presentation, also putting some order in everyone's thoughts, because we all struggle with these definitions. Maybe a first question I would have, I very much like the separation of biases. And sometimes what we struggle with is whether they are all clearly distinguished. For example, I would think inductive biases is anything model related, or up to now, that's how I use the term.
Yeah.
Can you really separate inductive from learning bias? Because also in your slide 39, they're a bit intermixed, right? I don't know if there can be.
Yeah, so.
Or what is a subset of the other?
Yeah, no, and that's a very good point. And indeed, I see your point. It depends also how you implement them in a way. So
in the way in which I understood you presented it, you would call inductive what is hard coded and maybe a priori in the architecture.
exactly.
And I think you mean learning is something of a more loose constraint, therefore the loss is also part of that.
Exactly, in that sense. So, but in a way, because you can think about it, it depends on which architecture you're using, right? So I think that in the neural network architecture, these two somewhat actually come together very easily.
I think in your slide they were also
exactly,
and that's where I think it's hard to distinguish between them, but maybe it's nice to have a way of thinking of them as perhaps something that's more hard coded rather than fluid.
I think that it might be useful to make them distinguished because the way in which I see it is that this come from some prior assumption and some things that you know. In a way, these are coming from the fact that you now decided how to do your inference, and now you want to select some of the things that come with their inference model, if you see what I mean.
So even if the model of the physics is given, you mean that the laws, for example, could have different ways of being expressed.
Exactly.
And therefore, it's still not hard coded. It's a selection. This is how you separate it.
Yeah. So that's what I was thinking about that, especially also because if I think about learning biases, you can even say the optimization parameters may be constrained to just look into the search space. That is not necessarily related to physics assumption that come from a constraint in physics. That come from something else. So if you think about phi Cindy, there we will have an inductive bias. So that is coming actually from the physics constraint.
Which is your library.
Exactly. Yes.
But is the fact that you chose a library that is usually solved with a list with a sparse regression, a learning bias?
And I know, and that's again when I think that the two can be mixed, and it depends how you see them. But I think that at first I would rather have them distinguished and then put in a model in a clear way, because I think that if you just say inductive, then it becomes too much to understand the one.
Exactly what's contained.
Yes, exactly. Thank you for this question. It was really great.
Marcus, yes,
I see your hand. Sort of, again, thank you very much for the talk. It's super nice to hear it explained in that way. It's definitely helped clear up my mind for sure. So for these two, again, between inductive bias and learning biases, could you sort of see them as almost the stages in the process? Because inductive biases is saying what the prescriptions are.
Yeah.
Learning bias is how you meet those prescriptions.
Exactly. I think that this is probably the best way of seeing it, because in a way, indeed, these are the things that you know and what they are, and this is how you implement them. So in a way, you can see it in this way, but they will be linked to the learning algorithm that you're choosing as well.
Yeah. So like if you had like a network-based one, and then with boundary conditions, the boundary condition that you set is the inductive bias, but then if you did it like in a hard fashion, so you just match the output, then it's no longer really a learning bias because it's just set.
Exactly.
Whereas learning bias is then, okay, it's a loss function.
That's it.
With the dictionary approach, it's like the inductive bias is the design of the dictionary.
That's it.
And the learning bias is
the sparse regression.
Exactly.
Like
I agree. That's why I brought the sparse regression as the example, because it's on the dictionary.
I know, exactly.
But it's true, it's a good way to separate how you meet the specified model formula.
Yes.
Are there questions also? There are a few.
Please.
Let me say that if you're online, I will give you the floor after maybe 2 questions we have here already. So I don't go.
Thanks a lot, Alisa. Great. I was wondering, so like it's here model for uncertainty and then model error, how to quantify it in general is a very difficult topic.
I know.
Would you think that physics and constants in learning provides ways to tackle this or to quantify it in a better way?
And that's the thing, in a way, physics and machine learning is helping you also distinguishing the different sources, if you think about it, because then you have also a clear way of thinking. You're coming from the physics, and then you have maybe an unknown functional form that you're learning from the data, but you still have some other uncertainties. So actually, probably it's better to go back to this slide very briefly. So my hope is that a physics enhanced machine learning framework will help us untangle all the different errors. and help us untangle all the different ways in which uncertainties will come in, such that then we can build a better, basically, digital twin or better model of the structure. But I must say that in a way you can think about it, we were already doing most of this. We were already doing most of this, but integrating all of it with the goal of guiding decision making. I think that that's still one of the biggest challenges.
But on that theme, actually,
Yes,
I think an issue is many of us, also myself, I have shown that it's good to think about error as superimposed to the model form.
Yeah.
And that's always correct, actually. What is failed to be stressed is that you may have a model form that is tunable.
That's it.
And so it's nice that you mentioned these known unknowns and unknowns, because this stresses this kind of, the value of that, because, and that's where physics enhanced machine learning obviously should be classified in terms of its ability to recognize a tunable model
Exactly.
form, or dump everything in an error, because I may have a linear model which is appropriate,
That's it.
but just slightly off parameters, and again, you can write it as the model in discrepancy, but that's not as informative as learning the parameters.
That's it. And
So it's
especially
nice to separate actually between.
nice, thank you, guys. Yeah, it's good. You can ask the question to Eleni directly. Eleni is
I
giving an
think
amazing answer.
it's related to
Yeah,
this
yeah,
slide,
yeah.
actually.
I think it's this one. Yes.
Can I get that slide, Alice?
Yeah. Sorry for that. Apologies.
So I need to leave, I have a question.
I will send you, I will link it
Yeah, I
to,
mean, next month I will submit a paper on friction models.
Ah,
We developed one with that additional three variables, so I think I have a lot of things work.
let me link you
Nice.
through email
Yeah,
then,
we're
since you have.
discussing shared data and method maybe.
nice.
Yeah.
Awesome. Thank
Thank you,
you.
Sergio.
Ciao.
Are there questions online? Because we cannot see it. You could unmute in that case. That would be sufficient, probably more efficient than me looking for raised hands, just to say this. Until then, any more questions for Alice?
1,000 of them. Yeah, me too.
Yeah, of course, we're nearing the end of the seminar. That's why I'm not going to push you for more questions. Let me give a last chance to the online audience. Is there a question you would like to ask to the speaker? If not, what I typically do is I give you the floor and you tell us what you want to leave us with as the main message of the talk, let's say.
You should all come to ETH and have a fun time with the group here.
Yeah.
They are amazing.
Oh,
They are
okay.
gonna show you all the things that they are doing that are unbelievably good. So I think that
This is an advertisement. for us.
no,
Yeah,
honestly, it's
I'm gonna-
really great.
Okay.
Yeah.
Thank you very much.
Thank you so much.
Thanks so much. And thank you everyone online for joining us. I will now officially
Thank you, guys.
pause the recording.